Science and Mathematics. It's my pleasure to introduce Dr. Matt Ikle, who was on sabbatical last year, I guess, at this time, in Hong Kong, working on some artificial intelligence. So please help me welcome him.
Hi, as Matt just said, last year I was on sabbatical in Hong Kong, working on artificial intelligence and some robotics while I was there. So this what this talk is going to cover. Since I spent the time in Hong Kong, in order to talk about AI and robotics in Hong Kong, we first have to get there. So we're going to do a little bit of a time warp here and enjoy a little bit slice of Hong Kong to begin with. Wait, is the microphone, it's not coming out of the speakers, or?
It is, it's just not very loud.
Is there a dial on the podium?
There is, but it's not. I'll start it over. That's just coming from the laptop. It's supposed to come through the speakers, but.
Flying that, Matt?
Why were you the pilot? So that was a quick 2-minute overview of life in Hong Kong. So the outline of my talk, we just covered the life in Hong Kong section. I'm going to talk a little bit about where I worked, which was at Hong Kong Polytechnic in Gino Yu's lab. I'll introduce a few of the individuals with whom I worked. And then I'm going to go on from there and talk about the project I worked on,
which is called OpenCog, which is an open source framework for what's called artificial general intelligence. I'll do a brief overview of some robotics that is happening out at Hong Kong Science Park by David Hansen, who founded Hansen Robotics. Actually, just before I left Hong Kong, they got an infusion of funds there. Then I'm going to bring what I talk about in Hong Kong back to what is going to be happening here at Adams State through a grant that I was working on as I was not in that plane, but in a plane going over for my sabbatical, and upon my arrival back in Alamosa, I found out that the grant was funded. And then we'll finish with some work that is going on that we did in a new class that I'm teaching this semester with some of my students. So I'm going to start off. This is the building where I worked at, brand new building in Hong Kong Polytechnic. I was on the 9th floor, if you can figure out which floor, the 9th floor there. It's called the Jockey Club Innovation Tower, and there's kind of an interesting thing here. Jockey Club is the betting for horse racing. You go to the Jockey Club places to place your bets, and evidently they make enough money because they that's where the money for that tower came from. So this is the lab in which I worked. So a few of the people from left to right, Mong on the far left was an intern. I never met the next guy there on the left. Ray Ting in the lime green, that's Ben. Ben's on the far right here, that's his wife. Mandeep from India was one of the roboticists there, and behind him from ICOG Labs in Ethiopia is Miskana, who is working in OpenCog. The tall guy in the middle, his name is Aaron from New Orleans, and he's working on natural language processing. And then you have William Ma and Ma Hing, and they are local from Hong Kong, Hong Kongers. And Ben Gertzel's really the team leader. I've been working with him for over 2 decades. And then you can see on the far right is a robot. The body is actually a toy. It's called Robo Sapien. We might be purchasing some of those. They're like $80 at Target. And the head, what does the head look like?
Einstein.
That's an Einstein, miniature Einstein head built by David Hansen. So, so I want to distinguish here I mentioned artificial general intelligence, and the difference between what's called narrow AI and strong AI, or artificial general intelligence. Narrow AI is basically solving tasks in very specific, constrained, narrow domains, whereas AGI is really the original goal of AI back in 1956. This is the 60th anniversary of what's called the Dartmouth Conference, because it took place in Dartmouth, with some of the main founders of modern artificial intelligence. The original goal was the construction of thinking machines that are able to learn general tasks, not just one specific task. So a couple of examples here. Back in 1997, IBM's Deep Blue became the first computer to beat the reigning world chess champion, Garry Kasparov. More recently, who's heard of Google's AlphaGo? So quite a number of hands went up there. So Go is an ancient Chinese game. It's considered vastly more complex than chess. And by vastly, I mean several orders of magnitude more complex. Anybody knows the outcome of what happened with Google DeepMind's AlphaGo? Randy?
Yeah, they just won like
5 out of 7, 6 out of 7.
More update on that.
Let's see,
It's
6
4
out
to
of
1.
7.
4-1 now.
4 to 1. So the difference, they're both really still narrow AI, but IBM's Deep Blue really just kind of did a brute force search method, as deep as it could go, to try to figure out what plays it would make. DeepMind was acquired by Google about a year and a half ago or 2 years ago, something like that. And their strategy was a little bit different. It's a little more general. They couple what's called deep neural networks with reinforcement learning. So that just gives a little bit of flavor. It's still specific to playing Go. Basically, it played Go with itself many times and adjusted weights inside the deep neural network. So since I'm going to talk about OpenCog, it's actually distinguished from that narrow AI paradigm in that it's going to try to learn how to do new tasks that it's never seen before. An example of that would be, say, a robot enters a kitchen it's never seen before. Can it figure out how to find the ingredients, find the water source, and use the coffee maker there to make coffee? Okay, that would be a more generally intelligent task than playing a game that it has seen before. So here I'm distinguishing 4 main approaches to artificial general intelligence. The first one, universal AGI, that's a very mathematical, theoretical, infinite number of resources type. It's kind of theory of artificial general intelligence. The next 2, we have symbolic versus emergentist, and sometimes emergentist is also called subsymbolic. So by symbolic, I'm thinking of things like we are going to label concepts like cat, like dog. We're going to think about these objects. And if you think in a computer science setting, graphs being nodes coupled with links connected by links, so circles connected by links, those circles would be labeled cat and dog. In the more symbolic approach, this is the basic idea of what's called neural networks. You again can think of these circles and arrows between the circles, but now the circles aren't labeled. They're just models of what's inside our head. They're basically models of our neurons. And where the concepts of cat and dog would come from would be the patterns that are formed from these connections, rather than the connections being labeled as certain concepts. I don't know, is that distinction fairly straightforward? Stop me with any questions at any stage here. And the last approach is what's called hybrid AGI. And any guesses what hybrid AGI would be? I call it the everything but the kitchen sink, or perhaps including the kitchen sink approach. Using emergentist ideas for some pieces, symbolic parts for other pieces, and so on. So the project which I've been working on, it wasn't called OpenCog before, but I've been working on OpenCog and its predecessors for quite some time, over 20 years. But OpenCog is an example of the hybrid approach. It's an open source framework initiative aimed at creating beneficial artificial general intelligence, beneficial in the sense that it would be helpful for solving problems that we find beyond our scope, problems of poverty, hunger, corruption, disease. So, this is the scary picture, right? This is just a portion of the architecture. So, you notice there's a big box in the center. And then everything outside is kind of interacting with that big box. That big box is called the atom space. That's where all the dynamics, all the patterns, all of that's happening. But I really want to really only pay attention, because that's what we're going to be concentrating on for the rest of this talk, and what's relevant for the internships, which I'll talk about at the end. The three boxes around the big box that are circled in red. So on the right, you have attention allocation. So from the name, what would attention allocation mean? Pardon? Where are you going to pay attention to, right? What ideas, what concepts, what reasoning rules would you be wanting to use to, for example, solve or answer some sort of query, right? If you're trying to determine the breed of someone's dog, chances are you're not going to worry about the concept of a trash can. You might be interested in concepts such as what's the weight of the dog, what's the size of the dog, what type of fur does the dog have. So those are going to be the ideas and concepts that you want your system to start paying attention to. And what kinds of rules and inference rules would you be applying to those features to try to determine the breed of the dog just based on your observations. So that's called attention allocation. In OpenCog, attention allocation is performed by a module called ECAN, or Economic Attention Network. And George Selman, a number of years ago, and I, along with some other individuals, worked on that. The two other sections, PLN, down at the bottom there, stands for probabilistic logic networks. It's basically a probabilistic inference system. What does that mean? Well, we're all familiar with standard logic, or should be, right? If A implies B and B implies C, then A implies C. But what happens if you think you know A, maybe you're only 80% sure, and, well, sometimes A implies B, and most of the time B implies C. What's your conclusion? Sometimes, what does sometimes mean? It's all kind of fuzzy, right, Christy? Okay. So we've worked out the mathematics here of a probabilistic inference system. And so that interacts with the atom, what's called the atom space, the big box in the middle there. And then up on the upper left is called Moses, And MOSES is another acronym. My students in AI can tell you what it means, but it stands for Meta Optimizing Semantic Evolutionary Search. It's a different kind of learning mechanism. Uses what's called hill climbing for searching through procedure learning. And so those are going to be 3 of the main modules that I'm going to talk about moving forward. So within OpenCog, and this is just using those 3 modules I talked about, there's this concept we've developed called cognitive synergy. And here's the idea, right? So when you're trying to solve that query of determining a dog's breed, right? Well, you've got your reasoning system, your probabilistic reasoning system. It's going to be coming into play. How can I, given the facts that I've observed, how can I perform my reasoning, my inference, to get to my conclusion? But the search space, where anybody in math and computer science can guess, does what? It becomes large really quickly. So what is that attention allocation? The idea of attention allocation is to limit that search, to concentrate on the observations and inference rules that have proven to be useful when performing similar searches. So the idea is to use attention allocation to help guide probabilistic reasoning, or similarly to guide procedural learning. And there's also the arrow connecting MOSES, meta-optimizing semantic evolutionary search, try to say that 5 times fast. And PLN, when one gets stuck, the other can help it as well. So within OpenCog, all of this framework, all of these modules, all of these ideas, we're using, in order to test them, we're using 2 different platforms for our experimentation. The first one, which goes back about 5 years, or at least, to around 2011, 2012, is to use the to create artificial intelligence video game characters that are navigating through a virtual environment called Minecraft. It's funny because on Monday, Microsoft just announced that they were going to create artificial intelligence characters navigating in the Minecraft world. And the other way, which we're working on much more aggressively right now, is a collaboration with David Hansen. You remember the Einstein head of Hansen Robotics. And so I have a couple pictures here of some robots. So in the big picture on the left, find the robot.
Yeah, it's right up in front.
Right? So this is Sophia. And then up on the top right, this was some cell phone video I took a year ago. This just came out. Sophia just came out in that complete form. So that robot, his name is Han.
Huh. Look at that. Ooh. Yeah.
So here's really the big picture that I want to talk about because it's more relevant, is what does that mean for our students here? As I said, the Army Research Office funded a grant. I found out about it, when was it? Around June, May or June of last year. It's a 3-year grant. It's worth over $500,000. It's going to pay for 4 research internships over the summer for 3 summers. It's basically continuing the work that I started or continued in Hong Kong for my sabbatical leave. The student support in this package is over half of the total value of the grant. And then we also later obtained a supplemental grant to also involve 2 high school students into the internships as well. So the internships basically follow 2 tracks. There's basically the AI OpenCog software track, basically continuing this work. If you remember the triangle of attention allocation, PLN, and Moses, the ultimate goal there is integrating those. Moses, in the original grant, we talked about integrating Destin, which is a visual processing system based on deep neural networks. That's still to be determined whether I'll switch that out with Moses or leave Destin in. But throughout the work, I'm going to be aided by George Selman and Comfort Cover of ASU, and each year the team will travel to a conference. And so I'm going to just quickly outline what's going to happen in each of the 2 tracks over the course of the grant. So notice there's this integration of the attention allocation and the probabilistic reasoning system. That's going to continue in the AI track. On the robotics track, it's really learning about our platforms, developing some software to integrate with the AI track later on. In the second year, we're going to then integrate the 3rd component with the first 2, attention allocation and probabilistic reasoning. The robotics track is going to take a different tack here, because here the idea of the grant was to pursue social and emotional robotics, which means trying to understand how, for example, humans express emotions, how they interpret emotions, how they use that for social interaction. So that's going to be a little bit different feel to it. And then year 3, any guesses on year 3?
Bring it all together.
Bring it all together, merge the 2 tracks. And as part of the grant, we agreed inside the grant that we would offer a couple of courses each year. I've been updating our artificial intelligence course to incorporate some robotics at the end and to incorporate some of these ideas. I've been trying to give a big picture, hopefully not too detailed picture, but in the AI class. And then as of this semester, we introduced a new course, thanks to Matt, Introduction to Humanoid Robotics. And with that, I'd like to invite the students from that course, Introduction to Humanoid Robotics. They have a robotics demo.